In our last video, we met the concept of a representation of a group, which is a way of taking a bucket full of matrices that walk and talk and quack just like the elements of the group itself do. And since matrices give us a lot of tools from linear algebra that we can work with, we hope that a representation can be a really useful tool for studying scary, abstract, weird groups that have behavior going on that we might not understand. In this video, we want to ask the question, just how good of a story do those matrices in a representation tell us about the group that they're representing? Can representations always reproduce all of the differences and intricate structure that exists within the group that they're representing? We want to be guided in this by the two examples from the previous video. First of all, we looked at the groups of permutations on n symbols. This is the same thing as the anagrams of n-letter words. And we developed a set of n by n matrices that are capable of behaving just like the generators in the Coxeter representation of the permutation groups. In other words, the adjacent transpositions of two neighboring strands in a braidogram. To do that, we use this magic 2x2 block matrix 0, 1, 1, 0. Because after all, the action of that matrix on a pair of coordinates is it just transposes those two coordinates. And when we place it in the context of a larger matrix on a block diagonal, we can create matrices, n by n matrices, that act just like these generators do. They have order 2, and they satisfy the disjoint strand and skein relations, just like the generators do in the Coxeter representation of the permutation groups. On the other hand, we were also interested in the braid groups, which are just like permutation groups, just a little bit more interesting, because where the generators of the permutation groups, these 0, 1, 1, 0 swaps, had order 2, the generators of the braid group have infinite order, because if I twist a pair of adjacent strands in a given orientation and then I keep twisting it and twisting it and twisting it, those twists don't undo themselves. They in fact just keep compounding on themselves. They never go back to the trivial braid in that case. And so what we expect is that since the presentations of these two groups are so similar, the representations, the n by n matrices we could use to represent them, ought to be pretty similar as well. We just had to soup up the braid group example by introducing an indeterminate variable t, which when t is equal to 1 reverts us back to the permutation case. But when t is not equal to 1, we get these matrices that have entries which are Laurent polynomials, positive and negative degree polynomials in the variable t in all of their entries. And we get a 6 by 6 representation for braids on 6 strands, or an n by n representation for braids on n strands. That's called the Burau representation. The Burau representation is how we use these matrices with Laurent polynomials in them to represent the generators and therefore all of the words that we can make inside of the braid group. And they satisfy all the relations that the elements of the braid group, the generators of the braid group in this presentation, satisfy. So the reason we should really like representations is that they offer us an opportunity to take some nasty, complicated structure, like a group that we don't yet fully understand how to work with, or a big bucket full of different knots or rational tangles or something like that, and exchange difficult questions that we could ask in a difficult setting for simpler questions that we can ask in a more familiar algebraic setting. We trade out groups, tangles, knots, whatever. We trade those out for matrices or polynomials or just numbers, right? Things that we've spent our entire mathematical lives studying how to work with. So anytime we could try to translate a question in a difficult setting into a question in a much simpler setting in which we have a lot of tools that we know how to work with, that's a good idea. But the big question that we're trying to ask ourselves in this video is anything getting lost in that translation? Are we always able to trust the story that's being told to us by the matrices that we're working with over here on the representation? Does it always tell us the same story as we would be told if we were working solely in the more complicated setting of the, for example, group that we're trying to understand better? Well, the first thing to know is that every representation is required to represent the elements of a group by matrices that at least satisfy all the same relationships with one another as the elements of the group did, right? And algebraist says that there's a homomorphism, a structure-preserving function from the group elements to the matrices that represent those group elements. So there at least has to be some reflection of the complicated structure within the matrix structure. In other words, every representation, because it's a function, has the property that if two things in my scary setting are the same, then they must be represented by the same matrix over in the land of matrices, right? In my example here, Fred and the Scooby-Doo villain are being represented by different matrices, but then another object which is actually the same object, so the Scooby-Doo villain with the hood over his head, right? Those are really the same object inside of my group, and therefore they must get represented by the same matrix at the end of the day, because representation is a function, right? So representations are always sensitive. The same object, regardless of what disguise that it's wearing inside of our scary setting, the same object will always be represented by one and only one matrix over in matrix land. So at least we know that for sure, right? Even though this presentation, 1-3 composed with 2-4 for a permutation of 4 symbols, looks different than 2-4-1-3. They're represented by the same matrix no matter what representation we choose, because in fact they are the same element in the permutation group of 4 symbols. It's the converse question that gives us the keys to the kingdom if we can answer it in the affirmative. If I have two different tricky things, will they always be represented by different simple things? So if I find a difference between two simple objects in my algebraic setting, does that always reflect a difference in the objects from whence they came back in my original setting? And vice versa, if I find two same values over here in algebra land, do I know that they must have come from the same element back in the scary setting of groups or knots or tangles or whatever they came from? Do different tricky things necessarily get different simple algebra things? And the answer, unfortunately, is no. And one of the quickest ways to understand why not every representation turns differences into differences. Just imagine a representation that takes every single element of my group and just assigns to it the real number 1, or the integer 1, under the operation of multiplication, for example, right? So this will still be a representation, and the reason this is still a representation is that regardless of what relations might exist between the elements of my group back here, all those relations, remember, are just words that evaluate to the trivial element of that group, right? So they are words that we can cross out and cancel. But if I'm sending everything to 1, and the operation is multiplication over here on the right-hand side, 1, no matter what combination of 1s that I multiply together with themselves to reflect the relation that exists back in this group, that product will always equal the identity element over here in algebra land, which is 1 itself, right? So I stick a bunch of 1s together, I'm always going to get a trivial word over here on this side. So regardless what my trivial words were over here, they will remain trivial over on this side, now that we've assigned 1 to everything. So what we are doing in this representation is we're constructing a representation, equal tricky things are still getting equal algebra things, and all the relations are still satisfied. We're just collapsing all of the differences that existed between the elements in my original group, because we're collapsing them all to the same number 1 in my representation. So it's not a very useful representation for telling the differences between elements in my tricky setting, even if it is a valid representation nevertheless. We can check that it's valid because, for example, if this is my permutation group on 4 symbols, right? This generator right here is an element of order 4 in that permutation group. So this element to the 4th power is equal to the identity element. Meanwhile, 1 to the 4th power multiplied by itself 4 times is going to give me 1, which is also the identity element over here. So that still works. In the permutation group, this squared is equal to that. And over here, this squared is equal to that. So this is still a representation, it's just not a very useful one. It's called a trivial representation for obvious reasons, right? It doesn't do a very good job at all of telling the differences between elements in my original group, even if it still somehow reflects some fundamental structure, that all the relations are still satisfied. It's just not a very interesting way to do it. So this is an example where we can get the same algebraic objects over here in algebra land that are representing different elements back in my scary group setting. So what we'd like to do is we'd like to look for examples where this doesn't happen. We prefer representations that can, in fact, differentiate between different elements, because representations in general aren't able to do so. If we can find a representation that does assign to different elements of my group different algebraic elements to work with, different matrices, for example, then that's a very special setting. It's the setting that we get when the function which assigns group elements to matrices is a one-to-one function. And when that's the case, the word that we give to the representation is that we call it a faithful representation. So a faithful representation is one that is both sensitive, because every representation has the property that it assigns the same algebraic object to the same tricky object from back in my group structure, but it's also specific, so that two different elements of my group are represented by different matrices when my representation is faithful. And that's a glorious place to be, because then any difference that we detect in the algebra setting, the simple algebra setting with matrices, must have been a legitimate difference back in my group that I'm trying to understand better. So if we have a faithful representation, we are getting a complete Xerox copy of the group over in matrix land. The good news about our permutations is that the left regular representation of the permutation groups that we've been working with is indeed a faithful representation, no matter how large is the set, the finite set that we're permuting. So no matter how many symbols, how many letters are in my word, my anagram, the left regular representation we get by using those 0, 1, 1, 0 blocks on my diagonal for my generators is a faithful representation. So as an example of why we might care about that, right? I build some nasty braidogram that has, you know, a dozen plus different transpositions in it in this diagram. And so it has this word written using the generators of the Coxeter presentation of the symmetric group on, in this case, 7 symbols, right? And then somebody else comes up to me on the street, because this happens to mathematicians a lot, and hands me another word built out of the same generators, right? And so they have different looking braidograms and very different looking words that are spelled out using the same alphabet. But if we crank through using the left regular representation, the 7 by 7 matrices that we would multiply together, if we multiplied all of those 7 by 7 matrices together and all of these 7 by 7 matrices together, it turns out that their products give us the same matrix. And because the left regular representation of the permutation groups is in fact faithful, that means that having the same matrix representing them must mean that we had the same element in my group that was associated with it, right? So a faithful representation has different matrices for different elements, and also if we have the same matrix over here, we must have the same elements back there. That's the beauty of a faithful representation. So if the matrix is the same, that means that the group elements must have been the same. And it would have otherwise been pretty challenging for me to use the generators and relations, the presentation itself, to try and rewrite the algebra of this huge word in the Coxeter presentation into this other huge word in the Coxeter presentation. So having the matrix and having a faithful representation really gives us everything that we need to trade a very difficult algebra presentation word problem into just a problem about compute this 7 by 7 matrix, compute this other 7 by 7 matrix. If those matrices are the same, then because of faithfulness, the group elements must have been the same. And so these words actually have the same meaning, which we could also check just by investigating the anagram that might result. If I take a 7-letter word like medical and I run it through each of these 2 braidograms, we could just trace those strands through and figure out that the word medical turns into the word claimed in both cases. So there is another verification that indeed these 2 braidograms represented by these words in the Coxeter presentation of the permutation group on 7 symbols are indeed the same element of that group. So having a faithful representation is a really, really wonderful thing. So what do we know, if anything, about the braid groups and their representations? This is where things get really interesting and a little bit scary. So we want to ask this question about the Burau representation. Is the Burau representation, using the Laurent polynomials with the indeterminate t inside of our n by n matrices representing the braid groups, is that a faithful representation? Do these Burau matrices tell the entire story of the algebraic structure inside the braid groups? And the answer, it turns out, is that it actually depends on how many strands that we're braiding together. This is actually a pretty long story in the study of the algebra and topology of braid groups. So if we only have a couple strands, if we have braids on 2 strands or braids on 3 strands, it turns out to be a pretty simple, straightforward picture, right? Braids on 2 strands, we only have a single generator inside of that braid group, and that generator is a positively oriented twist on the only pair of strands that there is. And we associate with that generator this matrix, T0, 0, 1. And you can check that when I multiply that matrix by itself, the only thing that starts to happen is that the powers of t start going up. Right? If I multiply it by itself once, we get t squared 0, 0, 1. The braid that I've sketched here on the screen has a total of 4 of those generators in it, and so the matrix of that braid is t to the 4th, 0, 0, 1. And it's not too hard to convince ourselves that that representation of braids on 2 strands being represented by these 2 by 2 matrices in this particular fashion is indeed a faithful representation. So whatever story is being told by the matrices that are generated here is exactly the same as the story that's being told by the braids themselves. It turns out that the same is also true for braids on 3 strands, even though the matrices start to get a little bit more interesting. Right? There's 2 generators for the braid group on 3 strands, right? The positively oriented twist of the first pair of strands that we'll represent with this matrix, again using my funny Von Jones bowling alley building block here, 1 minus t, t, 1, 0 in the first and second rows and columns for my first twist, and in the second and third rows and columns for my second twist generator, right? Positively oriented. And so it turns out it's been shown that this 3-strand Burau representation is also a faithful representation. But as people started to study this more and more, they kept asking the question, well, is it still faithful if we have more strands? Or at some point do we lose the tune? Do we have so many strands that we can create a braid of such complexity that these Burau matrices are no longer able to differentiate between different complicated braids with a ton of strands in them? And so here's an example of a nasty braid on 6 strands that actually has 44 different generators that make it up. It turns out that that nasty 44 generator braid on 6 strands actually has the same Burau matrix as a completely untwisted, untangled set of 6 strands. In other words, the trivial element of the braid group on 6 strands. The trivial element of the braid group on 6 strands has the same Burau matrix as this definitely non-trivial, so we would have to prove that this is actually non-trivial, but this definitely non-trivial element of the braid group on 6 strands has the same Burau matrix as the trivial element does. And so something has happened in between my faithful representations on 2 strands and 3 strands and my representation on 6 strands, which is definitely not faithful now because we have 2 different braids that are represented by the same matrix, i.e. the identity matrix in this example, right? And so according to this result, if we believe this result, then the Burau representation is not faithful for braids on 6 strands. That was proven in 1993 by Long and Payton. And that result was extended to the 5 strands case in 1999 by Bigelow at UC Berkeley. So these are some relatively recent results on how this works. So something gets lost. We gain so much complexity somehow in the braid groups between 2 and 3 strands on the one hand, which are simple and their Burau representations are faithful. The matrices tell the whole story. But by the time we get to even 5 and 6 strands, there's so much possible complexity in my braids that the Burau representation, the Burau matrices, are no longer sort of rich enough to capture all the algebra going on inside those braid groups. And you might notice that I've left one thing unsaid. What about 4? And the answer is, no one knows right now. It's 2020, and we have still not resolved the question of whether the Burau representation on the braid group on 4 strands is or is not faithful. You might imagine that one way of investigating this question might just be to build a whole bunch of non-trivial braids on 4 strands, compute their Burau matrices, which we can do with open source, widely available technology, as we'll do in our class, and just see whether or not we can make any non-trivial braid on 4 strands have an identity matrix, for example, as its Burau matrix, in the way that this braid on 6 strands did. If we could find an example, we could instantly be published and probably quite notorious in the world of mathematics. But no example has been found yet, and it's definitely not for a lack of searching. So whether or not this is actually a faithful representation is an active still area of research in the theory of knots in algebra. So it may be something that, that you want to explore in your later graduate studies as well. So the end of this story, I guess, just to wrap this up, is we've seen how matrices can be used to represent the structure of a group, as long as they behave in a lot of the same ways that the elements of the group themselves did. But very often we lose something in that translation from group elements over into matrices. If we don't lose anything, if the matrices tell the complete story, then we have a faithful representation. And any difference that we spot in the matrices must have been a difference in the originals. And any sameness that we spot in matrices must correspond to a sameness of the originals. But in general, we can't expect that to happen. Even though every representation assigns to the same elements in my group the same matrix over here in matrix land, not every representation is capable of detecting differences in group elements, because different group elements can in general have the same matrix that represents them. And so the golden key to the kingdom is a faithful representation where the matrix story is the same as the group story. We're going to search for those wherever we can find them. Just like later in the course, we're going to try to search for complete invariants of knots and links wherever we can find them. But they are much, much harder to find. And partial invariants, or general representations, not necessarily faithful ones, we can find those fairly simply, and they can still actually tell us a lot about the structure of the trickier groups and algebraic objects that they represent.